Okay, so the final set of end conditions we're going to consider is the fixed pinned column. So again, it's the same setup as we've seen previously with the schematic on the left, the deflected shape on the right, and then a free body diagram of a cut section of the structure on the very far right. The first thing to notice here that we haven't seen before is that we have, because we have a roller support up at the top, up at point B here, we have this reaction here. Now I've just arbitrarily drawn on that reaction without too much regard for the direction. As a result of that reaction up there, we also have this reaction down here. So that's something that's going to feature in our discussion. So we know that MO, when we do the sum of the moments about the cut, when we move on to do that, we know that MO is going to feature in there. So right at the very start, we can say, if I was to look at equilibrium of the column in the center diagram, I could make a statement. And that statement would be that the moment at the base is going to equal whatever the reaction is at the top times its lever arm of L, right? So I'm just going to state that at the outset because that's going to be handy for me as I move on through this process. In fact, it's going to be handy in the immediate next step. But that just comes from a very straightforward looking at the equilibrium of that particular structure. So we've stated that. Now let's kind of move on. So we're going to do the standard thing now, which is to look at the moment, determine an expression for the moment internally within the structure. And in order to do that, we look at a free body diagram of a subsection of the structure. And we take moments about that cut. So we're going to take moments about a cut right across here. So taking moments about that point in the structure, we have mx would equal m0 minus p times v minus, or times x. Now I told you that it would be handy to have an alternative expression for m0, and this is where it comes in. So mx is going to equal or times L minus p times v minus or times x. And so simplifying that down, we end up with our expression for mx, which is minus p times v plus or times L minus x. And subbing that into our differential equation of the deflection curve, we would have, okay, and we do our usual, we let k squared equal to p over ei for convenience. And then we're left with the following. You should see where this is going now at this point. Same procedure as before. We have a general solution that's made up of a complementary and a particular solution. And I'm not going to go through the whole derivation of that process again, but you can, and you should confirm for yourself that the general solution to this differential equation is the following. Okay, so now we're going to apply some boundary conditions. And again, this should be relatively straightforward. V, the lateral deflection of the column at the base of the column, is 0. The rotation at the base of the column, V prime, is equal to 0. And pinned at the top, so lateral deflection at x equal to L is also equal to 0. So these are our three boundary conditions. So we can go ahead and apply them in turn. So applying the first boundary condition, V at x equal to 0 equal to 0, that would yield 0 equals C1 times 0 plus C2 plus or L over P. Let's just label that 19. We would then say that the rotation at the base is 0. That's the second boundary condition, and that gives us C1 times K minus or over P equal to 0. Let's call that 20. And the third one, V at x equal to L equal to 0. And that gives us C1 times the tan, because you divide through by the cosine, and sine over cosine is tan of K times L plus C2. And that equals 0. And we're going to call that 21, right? So we've three different equations here. So our strategy here, first of all, is going to be to eliminate or from equations 19 and 20. So from this guy and this guy, we're going to eliminate that or. From equation 19, we could say that or is equal to minus P C2 over L. And then we can go ahead and sub that in to 20. And when we do that, we would get C1 times K plus P times C2 over P times L. The P's cancel out. That equals 0. And that would let us say that C2 is equal to minus C1 times KL. Let's call that just 22. Now, if we take this one that we've just worked out, this expression we've just worked out, and we sub that back into this guy, we'd end up with the following. K times L equal to the tan of K times L. And we're going to call that 23. So our task really is to work out the smallest possible value of KL that satisfies that equation. And the key thing to note here is that that must be done numerically. So we can't determine a closed we can't determine through an analytical method a value of KL that satisfies that equation. So you would set up a program, and indeed that's a good exercise for you to do. Set up a simple program, quick loop in Python or something like that, that will give you the smallest value of KL that satisfies that equation. So we're focusing here on column buckling, so we're not going to spend too much time on that. We'll just say solution of this equation gives the buckling load. And we'll also say that it must be solved numerically to identify smallest non-zero value that satisfies the equation. Now, when you do solve that numerically, it turns out that a value for KL of 4.4934 is what we're looking for. So subbing back in for K, remember K was the square root of P over EI times L equals 4.4934. And remember, that didn't come out of thin air. That came from the numerical solution of equation 23. And as I said, the value or the expression for the critical load drops out of that equation. And so we can solve and make P the subject of the equation, which gives us PCR equal to 20.19 EI over L squared. Now we have pi squared appearing in our other expressions for the critical load, so it will be helpful to get a comparable expression. So we could alternatively write that PCR is 2.046 pi squared EI over L squared. So that's what we were after. And what I'll say to you at this stage is you should use equations 20 and 22. So they were this guy here and this guy here. Use those two equations to confirm that the equation for the deflected shape for this column is the following. Alright then, so we've covered off pretty much all of the standard sets of boundary conditions. We've looked at the pinned, we've looked at the fixed free, the fixed, and now the fixed pinned. And we've worked out expressions for the critical load PCR and also the deflected shape for each of those sets of boundary conditions for the infinite series of buckling modes. So that wraps up all of the derivations that we're going to cover in this section.